It's now recording.
Thank you, everybody, for coming today to this really interesting webinar on OTEC viability as a catalyst for transformative island development. I'm going to hand over to Nick Lambert, who will be chairing the session. Nick, floor is yours, sir.
Thank you very much indeed, Steve. A real pleasure to welcome you all this afternoon, this evening, this morning, or whatever time of your day you're joining us, and a real privilege to introduce Professor Yasuo Ikegami, who is Director of the Institute of Ocean Energy at Saga University, and Ben Martin, who is a Project Manager at Xenesys. I may have got that in pronunciation, Xenesys, and he is also the General Secretary of the Ocean Thermal Energy Association. We've been exploring OTEC as part of the MARES project for the last 9 to 10 months. And I personally am a big fan of the capability, and the purpose of this meeting, this webinar, is to show that counter to some of the commentary that's out there, there has been considerable physical demonstration of the capability of OTEC and its potential scalability. And that is what Professor Yasu and Ben are going to talk to about us now. So with no further ado, Professor Yasu, thank you so much for coming on to speak to us today, and the same to you, Ben. You've got a lot of slides, so I'll let you rattle through them. When my ugly mug comes back up again on the screen, that'll be because you're getting close to a point at which we need to give time for questions. Thank you so much for joining us.
Thank you very much, Chairman. So we are very honored to the chance to our activities. So our title is OTEC Viability as a catalyst for the transformative island development. So OTEC stage is now new stage. So we would like to contribute to this renewable energy and carbon neutral. Next, please. So my name is Yasuki Ikegami, Director of the Institute Ocean Energy, Saga University, and Ocean Thermal Energy Association Executive Committee Chairs. So co-presenter Ben Martin, he is a manager, he is a OTEC plant owners, plant management, and he is a Ocean Energy Association General Secretary. He is a very key person of the OTEC operating and Kumejima model. Please next. Our presentation outlines first state of the technology. What is OTEC? Overview of OTEC and relative industry on the Kumejima. So Kumejima is a very keyword in our presentation. Kumejima for the small island model, mega scale offshore OTEC and industry, OTEC technology residence. Finally, OTEC implementation for MARES. So we believe the contributed MARES implementation. Please start the Ben-san.
So for those of you who might not know, we need to talk a little bit about what is OTEC and a little bit about the state of the technology, because not everyone's aware of what has been going on here in Japan. So this is where I'm located right now. I'm just in the next building over from this facility, which is on Kumejima. In general, ocean thermal energy conversion takes advantage of a local natural resource that's found in the tropics and subtropics. Generally, there's a natural occurring temperature difference between the surface and deep sea water. And so OTEC is a method of harnessing that temperature difference to create power. Such as in Kumejima here, locally, the surface of the water is more than 30 degrees right now. If we go down to a deeper depth, the water is naturally colder and colder. And so that temperature difference allows us to create electricity. The actual process for harnessing this is relatively simple. It's as simple as a steam engine, which has been around for a long time, where instead of using water as our working fluid, we use a low boiling point working fluid. We put that working fluid into a heat exchanger where it is warmed from the surface seawater. The surface seawater is naturally heated by the sun, so it's kind of like its own battery. The ocean acts as a battery where it heats that working fluid, creates a vapor. The vapor goes through a turbine, turns the turbine, which turns a generator and creates electricity. And then we also get more efficiency, more help from the deep cold water as well, because that cold water then turns that vapor back into a liquid and provides more kind of motive force so that that liquid can be reused again in a closed continuous cycle. And that's a really key benefit of OTEC, is that a closed continuous cycle means we can produce power 24/7, but renewably as well. So here on Kumijima in Okinawa Prefecture, the Okinawa Prefecture government in 2013 established a demonstration facility to use existing deep sea water intake pipelines to demonstrate this technology long term. And so this is a 100 kilowatt facility, which is equivalent to about 250 households of power generation. In Japan, our roadmap for development starts with this current demonstration facility, but our future goal is for an offshore large-scale facility with low-cost power generation at the 100 megawatt scale. To get there, we see two kind of branching markets and two branching opportunities. They both start at the next step of development, which is a 1 megawatt scale, which Kumijima Town here on Okinawa, on this island, is currently working towards. This opportunity allows for not just power generation, but uses the water resources in a variety of ways that are interesting for island development and for island security. And so this is the next step that we're currently working on right now on Kumijima. Potential for this technology is not worldwide. We need a temperature difference of generally what's considered about 20 degrees Celsius. So this is a vast area of the world where our traditionally underserved communities can have largest access to potential for this. So of course, Okinawa and where we are here in Kumijima is right at the edge of that usable belt, but there's a vast area where places like Indonesia, the Philippines, Oceania have really good access to this resource. And so this onshore OTEC combined with different industries creates a local resource that can help us address these global challenges we're seeing ever more strongly and needs increasing ever more dramatically from a single system. So the OTEC resource allows us to address energy security, water security, food and economic security, environmental security challenges, while also saving energy through things like seawater air conditioning. And so it's access to a resource rather than depleting the resources we have currently available. So I'll talk a little bit more about what we're doing right now and how that will apply to this image of island security that we are looking at. So Kumijima is located in the Okinawa Prefecture, which is the southern part of Japan. Okinawa Prefecture is a community of many islands. And like many of the island nations that are looking at this technology, we're 100 kilometers west of the Okinawa mainland, out on our own on this small island grid. So we have a population of about 8,000 people and an average power generation demand of about 5 megawatts. Our main interests are fishery and some agriculture, but we don't have a lot of tourism because there's other places that are more active. So the largest industry actually for Kumijima has become deep ocean water industries. So because we have access to this great deep water resource, we're able to produce our own products and actually export them as well throughout Japan. We've become the leader in several fishery products, as well as having growing demand for more production on this island as well. So to talk a little bit more what this resource that we're talking about is, what is deep sea water? So surface seawater is warmed by the sun. It's the natural seawater you see all around you, and it's a large part of the world's ocean and the world's surface. So it's a vast resource. But the rest of that water, the water you can't see, the deep sea water, is the larger resource. It's more than 90% of the ocean is deep sea water. So we consider anything more than 200 meters to be deep sea water. So that's cold, it's nutrient rich, it's clean. It's a great resource for a variety of industries that I'll talk about in a little bit. It's probably hard to see because it's small, but when you talk about ocean energy, you talk about offshore floating wind and tidal and waves, and you can notice that the resources that they work from, while vast, is just a small part of the total resource we have out there. So really, deep sea water provides a great opportunity for a lot of people, and it's been underutilized so far. In Japan, though, we have 15 sites that are currently using deep sea water throughout Japan, from all the way up in Hokkaido, where it's very cold, down to here in Kumijima. The uses of the water depend on the various properties of deep sea water that the industries are looking for. Some of it's industry, some of it's academia, and some of it's just research. But they go from everything from food to bathing to aquaculture to even mineral extraction and refrigeration. So there's many different ways we can use this deep sea water depending on the needs of the local community. On Kumijima, while we're isolated and far away, production has grown organically from the efforts of local people. So we currently have about $24 million a year in annual revenue from various industries that have grown up here, mostly from fishery, and also a growing area from cosmetics. Even through the pandemic, we've heard that the cosmetics and other industries have continued to grow. So we're now closer to about $30 million a year in revenue, which is equivalent to about 300 jobs, which is really huge for a small island community like this. So it's become actually the largest single industry for our island. Most of our land uses still for sugarcane. That only has a revenue of about $10 million a year. So we're far past the revenue from agriculture, just from a small scale footprint. So it's great for these island communities. As far as agriculture goes, Kumijima has long had the highest market share in Japan for kunma prawns, which are a type of shrimp, and sea grapes, which is a type of sea plant. And both of these are produced with deep sea water or deep sea water properties. Well, lately we have other industries that are coming online as well, with companies trying to increase the sustainability of their products, such as safe to eat raw oysters or different kinds of sea plants or even salmon. And so the deep sea water provides different benefits, such as bacteria-free water or temperature control that allow them to produce sustainably and safely, but also profitably, even on a small scale. And this matches, global trends where we see, this is just for Japan, but where you see the transition from fishery to agriculture. And that trend, we don't see stopping. So as we look to go onshore, we need new resources to farm safely and also provide food and feed for those products, and also then to manage that in a sustainable way. And so deep sea water has a great resource to help support that trend. Cosmetics can be produced from deep sea water. The clean resource allows for sustainable water production. The minerals also can be included with other local ingredients and create a great product that can be used both locally and then also for export. So currently our local production company does OEM, providing production capacity for other companies throughout Japan and also abroad as well. We also have a coral research and nursery. Because deep sea water is cold, it allows us to maintain the temperature control to produce onshore coral without the issues of bleaching, but also by maintaining the temperature and quality through heat exchangers and other types of uses like that. So it allows us to keep the environment safe and can provide great opportunities for production as well. Saga University has also established a small-scale flash desalination. Flash desalination is a desalination technology that uses a vacuum chamber to evaporate surface seawater and then condense it back into a liquid with deep sea water. This process allows for much less maintenance and easier establishment compared to reverse osmosis. And so these kind of technologies are also being demonstrated here on Kumijima, and that has the potential to, in the future, be expanded into hydrogen production as well through electrolysis or similar technologies for future off-scale demonstration. Development continues with new companies coming in to use this deep sea water resource in new ways. One of them is Lot Pharmaceuticals, which is a famous healthcare provider in Japan. But they're also looking at ways of helping social health and sustainability. So they are using the deep sea water resource to grow different kinds of phytoplankton, both for primary production, but all the way through tertiary production through additional industries such as craft beer production, also sales through their local cafe, so that they can model the different benefits of using both deep sea water with energy in a variety of ways for island communities. And so for our view on Kumijima, we don't think of OTEC just as a single power production or single industry, but we combine OTEC with all these different potentials to create a kind of systematic approach to future energy. around the world, OTEC and deep sea water has been catching on. So within the deep sea water use, there's many different ways that we can use it, from seawater air conditioning to provide high efficiency, low environmental impact cooling, OTEC for power production, and low temperature thermal desalination for freshwater production. Throughout the world, there's now 38 sites with more than 45 pipes using this resource in a growing way. And this started in a big way in the 1980s in Hawaii. So now I'll talk about how we're integrating these different industries and OTEC for the near-term future for Kumejima. So because on Deep Kumejima, we have all these great uses of deep sea water, there's been more demand to increase the intake capacity and increase the amount of water so we can expand these industries. And at the same time, these provide the seed of what we call the Kumejima model, which is combining OTEC and various industries in a more efficient and smart way. So instead of using water just once in various industries, we want to cascade the water. We want to use the water multiple times so that we're not wasting this great resource. So we can use it in power production, but once the water leaves the power plant, unlike other fossil fuels, it doesn't become pollutant, it doesn't become a waste, it becomes a resource for us. In terms of deep sea water, as it goes to the facility, it's slightly warmed, and that warm water can be reused in things like agriculture or even in fisheries multiple times. So for Kumejima, and so for implementing this here and hopefully around the world, we expect to have at least a 1 megawatt OTEC facility powering this local community that enables also expansion of current businesses and technology demonstration and the opportunities for new ideas to come in and expand. And that's where I think MARES is also really kind of starting to think about how we use the ocean in new ways. This also feeds into Kumejima Town, the local government's look at the future, where in 2008, the mayor announced that they would work towards 100% clean energy. And to do that, they did an energy vision, looking at how the town could take advantage of the different technologies out there to get to 100% renewable energy. And how long will that take? So for the town in Kumejima, we have an average of about 5 megawatt load. And so our future looks to offset the current diesel power generation at a small scale with 1 megawatt OTEC as the next step. That will allow us to reduce the amount of diesel power using locally and also increase the number of amount of renewable energies we have on the grid without negatively affecting the grid as well. In the future, with an offshore facility, a total of about 6 megawatts of OTEC generation, we're able to go 100% renewable energy with both OTEC and solar and storage and demand response technologies in order to manage the grid. So this is kind of the view for Kumejima. And to implement this, then we look at how we put in this deep sea water and generation facility. So for us, we see deep sea water as separate business and intake that allows us to provide a resource for a variety of industries. And then these different industries can act as private sector businesses where they buy water from the distribution company and then can provide revenues back. And it creates a system where there is infrastructure available for the various uses, but also allows for OTEC and power generation to become a much simpler process. It's just a power generation company. It's just like any other IPP. And so it becomes a very simple equation in terms of energy. But it also provides benefits. So one of the benefits for OTEC is that as it supplies different temperatures, it can increase the ease for the different deep sea water industries and surface sea water industries to get the water they need and the water quality they want to produce their products, and also reduce the pumping costs and other issues that they would have if they tried to just put a pipe in the water on their own. So how much does this cost? So for us, we look at two kind of scales, two different markets that we have for OTEC. We have onshore and offshore. Onshore is considered anything up to about 5 to 10 megawatts. So 10 megawatts are larger because of the large scale of the pipes required. We expect that that needs to be offshore. And offshore is more difficult, but at larger scales, the economies of scale help bring down the cost significantly. So in the future, we expect a 100 megawatt power generation facility to bring in have a power generation cost of about 10 to 11 cents per kilowatt hour. And So then how do we address that short-term small-scale costs? So if we consider OTEC alone with the deep sea water altogether, and of course it's very expensive. It would cost from about the 40 to 60 yen or cents per kilowatt hour, which is expensive. However, if we approach this as we are doing in Kumejima, where deep sea water is an infrastructure project, a separate project, then we can reduce the capital cost in considering OTEC by reusing that water in multiple ways through different industries. And that brings the cost down really dramatically. If we're just talking about OTEC, then we're at the 10 to 15 cents per kilowatt hour level, which is competitive with the diesel we have on the island already. So that's a really attractive approach and something new that hasn't been kind of looked at in the past when we're talking about OTEC. So just to give you a general breakdown based on research done in Japan, several years ago, the new Energy and Industrial Technology Development Organization of Japan, NEDO, did a study based on OTEC. And so, adjusting to the current US dollars at 125 yen, we had a capital cost of about $24 million for an OTEC facility. If we include some of the capital cost for a pipe in that, we get a power generation cost of about 24 cents per kilowatt hour. If we separate those, if we make OTEC just on its own, a power generation project, we come down to about 15 cents per kilowatt hour, which again is attractive. And with the current kind of subsidies that are available, either with feed-in tariff or the different kinds of rates that are available, it can be an attractive even at this very small demonstration initial stage scale. And so for Kumejima, we're looking at how much, what are the benefits and costs for this? So in 2017, we did an economic survey looking at how much water can actually be used on the island, including with OTEC. And so these found that from a project perspective, it had a benefit to cost ratio of 2.115. And so that's a really great figure for us. It shows that there's a lot of benefit for the public from this kind of infrastructure project. And then in the future, as we go offshore, looking at the larger scale, this estimate doesn't include any improvement in maintenance costs that we found from our demonstration here on Okinawa, but we still have competitive power generation costs where potentially for this offshore 10 megawatt for the larger communities that need more power, at the 15 cents to 18 cents may be viable for even the early stage OTEC demonstration facilities. So now I'd like to talk about OTEC technology readiness and some of the challenges and opportunities that we have right now. So a lot of the questions we get is OTEC viable? So what about the deep water OTEC, deep ocean water intake? Onshore OTEC does require large intake pipe. And so it also requires a very long intake pipes. And that's where the major cost issues come from for onshore applications. At Nelha in Hawaii, they have a 1.4 meter intake already established. So it's an established technology. It's there. Kumejima, however, for our current small scale intake for this 100 kilowatt demonstration, we only have 28 centimeter pipes. So how do we then expand? Is it viable to do that? Well, for us, there are pipes throughout the world now. Just 20, 30 years ago, there was only a few locations that used these. Now, pipes, even in the deep sea water, are situated throughout the world, used for cooling hospitals in Tahiti, used for different kinds of cooling for resorts or fishery intakes and all kinds of applications. So it's an established technology. They're long-term, low maintenance, and it's a great resource. When we go offshore for large-scale pipes, HDP, the high-density polyethylene pipes, are now used for power production facilities around the world, and there's large-scale production and experienced companies that install them. There's also been work done for looking at larger-scale facilities when they go offshore. And of course, even for nuclear power now, they use very large intakes. Hinkley Point, which is just under construction, just recently installed very large-scale concrete pipes. And so there's a lot of other industries that are using these technologies that feed into OTEC and help offset a lot of the concerns that there used to be for OTEC. How about the power generation system? Is OTEC viable? Well, since 2003 at Saga University, which Professor Ikegami is the director of, they've had a small-scale lab using the technology and testing various cycles, testing various working fluids and different components And then this research was put into actual use here on Kumejima in 2013. And so from that, we've had long-term autonomous automatic operation in real-world environment. And we have that data that helps us look at the future. In the 1970s and 80s, there was initial work done in OTEC, both in Japan and Hawaii. And the evaluation was that OTEC is technically feasible, but not economical. That has changed. So it's in the spotlight again because there are technical improvements. There have been research that we've done that have improved that equation. A lot of that comes from, a lot of the industries that are working in the ocean. Just 10, 20 years ago, the deep sea ocean wasn't a very established market. However, now there's many facilities, many platforms, many technologies that are easily able to work in very deep waters. And deep water means that we have access to deep sea water. We've also done a lot of development on increasing the large-scale capacity of heat exchangers and optimizing them for OTEC to reduce the costs for OTEC as well. And so for commercial OTEC, the future major cost will be in these heat exchangers. So if you can reduce the cost of those by increasing performance, it has a big overall effect. So using our demonstration facility here on Kumejima, we've looked at the OTEC demonstration and allowed that to directly connect it to our future 1 megawatt, 10 megawatt implementations in order to accurately design and plan for those large-scale future implementations. So we already have, based on the current demonstration, designs for 1 and 10 megawatt facilities that can be quickly applied to other communities through adjusting to the local conditions. The heat exchangers that we developed and are testing here at the demonstration are directly applicable to the 1 and 10 megawatt scales by adding more plates, increasing the number of units. And so the data we have now is directly applicable to large-scale facilities. We also use titanium, and they're fully welded. So that means that we don't have any risk of mixing our working fluid with the seawater, so we can reuse it again in different industries. Titanium also has a very long shelf life, long operational life, which means that we can reliably use these technologies for 20, 30, 40 years, just like a traditional power plant. So while there is a large capital cost, the payback it can be quite advantageous. So is OTEC viable? And OTEC provide net power. Net power was demonstrated in 1979, but it was, of course, limited to the available technology at that time. One of the major improvements is that in the 1970s, 1980s, 70% of the power produced was used internally. That meant only 30% of the power would then be available for the grid. Today, with the current technology, we can produce about 70% of the power for the grid and use the remaining 30% for the internal piping and operationals. That means it's almost 2 times more baseload power for the grid, which means that power is available 24/7. So that's the biggest difference between the original OTEC studies back 30, 40 years ago and what's going on today. There's more power available. What happens when it snows? So on Kumejima, sometimes we get very strange weather where suddenly it'll snow up on the top of the mountain. So this graph shows a week's worth of data with surface water in red, deep sea water in blue, and the green is our ambient temperature. And you see that the temperature dropped about 10 degrees in just about a day or so. But the surface water doesn't change even 1 degree. So that's a natural occurring process where the ocean acts as a buffer. It's our storage. And so that provides a reliable resource for baseload power with a very high capacity factor. How about OTEC in the environment? So compared to traditional, fossil fuel facilities, of course, there's a capital cost, there's a carbon cost for the facility itself, but there's almost no maintenance, there's no fuel cost. So in Japan, we've done some research such as III evaluation of OTEC and Dow industrial use, looking at how does that OTEC facility affect the fisheries? Does it improve? And so with large-scale OTEC, we have a massive impact on the reducing ecological footprint from these kind of power production and fishery perspectives. We've done modeling to look at plumes because deep sea water is nutrient rich. And so if we put that nutrient rich back in the ocean, we need to do it responsibly, but it's also putting ocean water back into the ocean. So it can be done in a way that doesn't affect the local environment, but we've also done studies to make sure that that's true. And there's also been large-scale, plumes around the world of looking at, yes, we need to, when we discharge water, we want to make sure that we don't affect the coral environment. So because nutrients may affect corals, we want to make sure that the water is discharged past them. But there's also maybe a need for more environmental impact assessments for local communities as well, for small-scale implementation. We've done some demonstration already with not just OTEC, but also using OTEC and water in industries. So currently, right now at our demonstration facility, we believe it's the first time in the world that someone's been able to do this, where we produce power, we put water through our OTEC facility, but we also connect that water to both our sea grapes and oyster production as well. And so those are currently two ways of using the demonstration to inform future operations and opportunities. I'll pass over to Professor Ikegami now.
Yeah. Next, we would like to explain is OTEC valuable, so on social and economic consideration. Next, please. So this figure shows a comparative study for the selection for the renewable energy introduction for specific tropic island. Tropic island is very limited area and limited population. So we evaluate the with renewable many renewable energy. So the first footprint power generation. Solar required very large land used. So offshore, onshore, offshore wind is triangle. So wave and tidal. So OTEC is a large benefit because OTEC is very compact. For example, 10 megawatt solar power, so close to the 100 cents. So power generation cost, OTEC, of course, OTEC and onshore wind very benefit. OTEC is small OTEC is very high cost, but at least 1 megawatt OTEC is some benefit. So over 10 megawatt, so very close to the solar or below the solar power energies. And initial cost, OTEC is solar and onshore is large benefit. So OTEC is intake tube, very costly, but power plant is almost same. So, but if we intake tube supplied by infrastructure, public infrastructure implementation, so we this intake tube cost we can cover. So running cost is this result, solar and onshore wave. So OTEC is a running cost is no needs the fossil oil, and power stabilities. OTEC is constant, 24 hours stable, and no need storage. OTEC is no need storage, but another energy is very needed storage, electric storage. Capacity factor. So solar and onshore wind below the 20, but OTEC is 80 and 90% over. Next. So necessary for internal power is OTEC is needed internal power 20 or 40%. And employment creation, OTEC is combined used. And industry benefit, OTEC only benefit because not only electricity, spin-off and byproduct, OTEC is possible. And hydrogen is OTEC high benefit because OTEC is both product water. So water and electricity from the OTEC, we can generate hydrogen very cheaply. Next. So totally, we have proposed OTEC and solar combined. So when I mean the 100% renewable energy strategic combination, OTEC and solar power generation in effective SDGs achievement in tropic. Next, Ben-san, please.
So is OTEC viable? In short, yes, we believe so, because it hits all of the kind of necessities for island communities, and we've shown the full implementation at the small scale, but also that it can be worked at the large scale as well. So where can we do this? When viewing globally, the potential for OTEC makes it one of the most promising renewable energy sources for this huge area of the world, especially near the equator. On the other hand, it's not so easily accessible for places like the United States, Canada, a lot of Europe. And so the interest has been relatively limited so far. However, there are more than 90 developing countries and regions that have high potential, but they also need assistance to make it happen for them. So how do we see this happening for implementation for MARES? OTEC aligned to the MARES goals. So for Kumijima, what we're doing right now is a 1 megawatt scale. We're working, we have a projected start in 2024, looking towards installing a new pipeline to expand our water capacity in order to enable a 1 megawatt facility. This Kumijima model can be a real catalyst for MARES, such as an intake installation in some place like Palau, where a 2 megawatt OTEC facility would enable them to look at not just power generation, but all of the MARES framework. Essentially, OTEC would be the resource provider for a lot of the MARES framework ideas that have come out. And that can be scaled again through to the 10 megawatt plus scale offshore for larger communities, larger islands that need water. And then that power and energy and that electricity can be connected by cables or other technologies that are being developed very easily with the offshore wind communities as well. There's also a lot of OTEC and power to X opportunities. So a lot of island nations, they don't have access to clean water. There's a lot of concern about future, hydrogen and ammonia production. They don't have access to rare earths, rare metals. However, a lot of that's in the ocean. And so through OTEC, we can provide a variety of industries. Some of these can only happen onshore. Some of them can happen offshore as well. And so there's a great opportunity to look at, how does each community create its new economy from the ocean, from the deep sea water resource. So if we can create this model, create this method of installing a resource, giving back, to communities their local power, then it really changes island communities. And that's why I'm involved in this. Is I live here on this island, and I hope that this will be the base of my future kids' world. So OTEC, for Palau, if we are going to bring OTEC, what will it do for them? We can provide OTEC, of course, power generation. We can do deep sea water air conditioning. We can use desalination for water production, and water can be used in multiple ways for industry development. It requires a system approach, looking at the infrastructure to enable energy, water, and food, but it also creates baseload power that can help reduce the overall carbon load on the community by enabling more renewables to come in without offsetting the resilience of the grid. It can address the small community needs. It can increase the large-scale commercial deployment and also reduce risks. Professor?
Finally, so together, MARES and OTEC provides a new model for the island development, providing island and the coastal communities the local resources they need for the energy, water, food, economic, and environment securities. So from the MARES project, including OTEC, we believe that we can acquire the paradigm shift for the in the world for the sustainability and carbon neutral. Thank you.
You caught me out there, Ben, because you finished exactly on time, and it was perfect. What an excellent presentation. Thank you both very much indeed, Professor Yasu and Ben, for putting together that presentation in such a comprehensive way, and also for aligning it with the MARES approach, this holistic approach, and the power to X aspects. So I'm really grateful for that. I love listening to your presentations. So ladies and gentlemen in the audience, we've heard from Professor Yasu and Ben several times now, and each time I learn something new, and each time I walk away very enthused. And there are three things have stuck in my head from this one: the deep ocean water resource, that slide which showed the deep ocean water resource in compared with the continental shelf resource was an eye catcher. The method of making it national infrastructure to create a business model that works has really stuck in my head as well. And then 90 countries around equatorial latitudes, really lovely takeaways. I have some questions, but I'm just going to say to the floor, does anybody have a question, please? Please put your hand up if you do. And also, please do put comments and so on in the chat. I have a question from Yao. I probably pronounced your name incorrectly. Yao Duarte. Please ask your question and come up on camera as well.
Nick-san.
Hello. Thank you very much for your presentation. I'm from Portugal, and I just have two quick questions. Could you tell me more or less what would be the turbine ammonia suppliers existent in the world for this type of technology? If you're looking for suppliers, what would be the main ones?
There are both Japan and international suppliers. It's a generally relatively well used implementation for waste heat power generation, and also in geothermal applications as well. So I don't have a list of all of the providers, but we found that it would actually be much easier from a small scale demonstration from there's commercial applications from 1 megawatt and larger. So generally commercially available suppliers would be applicable for the turbines.
Okay, and last question, in terms of warranties of performance, is that easy to obtain? What would be more or less the standards for this type of technology in order to implement it commercially?
Right, so there is no commercial OTEC facility yet. We have 100 kilowatt demonstration, and so that data we have shows us gives us good expectation for how a commercial facility will operate. In order to get there, we need a larger intake pipe, which there is currently no intake pipe available for OTEC production, although NIL has one very similar size. So we feel that based on the demonstration of the OTEC, we can reliably operate at large scale with our technology. Because we're using titanium, there's no risk of leakage or rusting from the heat exchanger. So that's the major driver of the long-term kind of operational guarantee. We have experience in how does that seawater interact with the system, what are the issues in terms of fouling, and what are the maintenance requirements from that. And so we have a good handle on, what are the challenges and benefits for this type of facility. Ours is outside, of course, there's rust and environmental impact, but traditionally, if we put that into a building, that offsets a lot of that, concern.
Thank you. Thank you very much.
Thank you for the questions. Gary, you have a question?
Yeah, Nick, thank you. Ben, I probably posted my question before you got to that bit of your presentation where you talked about the local environment, but I'm keen to just understand. So from a ecological perspective, mixing the cold, deep water, nutrient-rich water with surface warm water, have you observed any detrimental impacts thus far? And I think you spoke about studies. Is your studies based on sort of analysis and assumptions and not so much so actual evidence at this stage of development?
So for here on Kumejima, we do return our water to the ocean. From Okinawa Prefecture's Deep Sea Water Research Center mixes the water and discharges it at a depth of about 25 meters, which is offshore, about 400 meters offshore, so past the coral environment. And they've seen there hasn't been a rigorous testing, so we don't have that data. However, anecdotal evidence from local people have found no issues. Actually, divers like to go and they take tours there to dive around the discharge kind of area. And so there's been no negative impacts that we've seen, but there hasn't been a real rigorous study either. There's generally samples taken from both surface seawater and deep sea water every year just to make sure there's no major issues going on. And then a lot of the studies have been more like modeling. Okay, so if this cold deep sea water is discharged, where will it go in that certain environment? And it's generally found that for large scale capacities, if it's cold in deep sea water, it'll sink. And so it'll quickly, go to an area where it return to its natural environment. In the near shore, of course, if we put that deep sea water into a coral area, there's concern that that nutrient could affect coral. So we want to make sure that when we do discharge, we do it responsibly, but it's something that can be managed and is part of an environmental impact assessment and part of the initial design of the system as well.
Okay, great. That's fantastic. Thanks, Ben. That's answered my question.
I think Agostino Miguel is typing a question. Ben, just talk a little bit. One of the presentations you gave, you talked about the system being a bit comparable with a nuclear power station, but without all the things that glow in the dark. And it sounds almost like Nirvana. And you've also said it is valid now. And one of the reasons we asked you to is to confirm that this is a viable, scalable capability was because a lot of the commentary out there is that it's still unproven, and that appears a lot, even in more recent press coverage. So could you just comment around that? It does look like Nirvana, and is it the sort of equivalent of a passive nuclear power station? And the other thing is, are you seeing the commentary out there changing? Is it? You said to me before that you've been demonstrating for 10 years now. Are you starting to see more up-to-date commentary, which is saying that yes, this is a viable technology?
So nuclear power is a steam power generation, but it's heat is from things we don't want to see near us, and so we have to put a lot of protection in to do that. For us, we're just working with the ocean. It's a natural resource. It's right. I can see it from my window. It's right next to us, and it's local. We know it. It's also something we need to use responsibly. But if we do that responsibly, it's just using a little bit of heat from the ocean. It doesn't take a lot out. A lot of detractors will say it's not efficient. It's not efficient. From a technical perspective, it's just it's not the most efficient system, but it's using just a little bit of the resource. So it means we're going to be able to use it longer, better, without affecting the environment, and it's always there. It's a natural reoccurring cycle in the ocean that's heated and cooled, and so it's very passive, as you said. We're bringing water up, we're turning it to the ocean, and we're using a little bit along the way, but it's a massive scale. 90% of the world's 70% of the world's surface is ocean. 90% of that ocean is deep sea water. It's something we have to use if we're going to address these global issues. It's a resource if we don't take advantage of, we're not going to be able to meet our global goals. But it's also something that can directly affect these local communities quickly. Now, in terms of, do people understand that this has been established? No, not everyone has it. Not everyone can come down and visit us here on Community. But the people who have, it does change their minds. You can see, the fish in the water, things that are being produced. You can taste it, you can feel it. You can, have some deep sea water beer for those who like that. So it changes your perspective. So that's one of the things we've done with this demonstration is allow people to come in, touch it. Kids can come in, they see it, they touch the facility, feel the cold, and that is a big impact. So if you're in 30-degree temperature in the tropics and you're feeling 9-degree temperature or less, it's a big deal because then you have the hot resource, you have the cold resource, you have something really magical you can create from that.
Yeah, and the 90 countries and the fact that the US and Europe are not, it doesn't suit their latitudes, and therefore the drivers, the sort of international drivers, are not there. Have you got a view on how we can get that engagement across the 90 countries in the equatorial latitudes? Is this something we've got to do through the UN, for example? Is it something that needs to be driven through banks like ADB or World Bank? Have you thought about that scalability by raising awareness, breaking down cultural barriers, and then how do we drive this debate to get something happening?
Right. So for onshore, when we've got small scale, of course, the pipeline's expensive. And so that's a big hurdle for small islands to overcome. They want the technology, but they don't have the resources to put in a big pipeline on their own. So how do we help them get that access to that resource? Well, one is we're looking at technologies that can hopefully offset this cost in the future in new ways. We're doing some research on that end. But for the existing technologies we have, it means every location is going to be a little bit different. So it's not something that's easily repeatable from island to island. And that's a challenge for businesses. If we can do the same thing 20 times, it's much easier. So this onshore small scale will be most helpful for the smallest, most needy communities. But that's also a stepping stone towards offshore. And once we go offshore, then that means that it can be repeatable. It can be the same facility done 20, 30, 40, 50 times, and then that can be scaled up as well. And once we get to the large scale, when we're at 100 megawatts, then we're talking about large scale energy production. It can be offshore, it can be anywhere that has access to that temperature. And that means that then we're starting to produce things that can be shipped, like hydrogen, ammonia. These things that the UN and the global markets are really looking at now. It could be one of the major energy producers for those commodities in the future. And so that's when that resource then can come back and be transported back and come back to these larger communities. So if they invest now in this technology, they're only reducing their costs and improving their time scale to get access to these kind of opportunities in the future. So I think once that becomes kind of part of the mindset, yes, we may not be able to use a small scale facility in California, but if we do this in places that need it, like Puerto Rico, who just had their whole grid wiped out again, we can be providing their power from the ocean right now with an OTEC facility that's not affected by typhoons. We've had Category 5 typhoons come over our OTEC facility, and it's still here. So we can manage those issues. And I think that's really kind of the key is, yes, the small island communities that can use the small scale need it now. They don't have the resources to do it on their own. How can we help them get it? So our perspective is if we can find this framework to enable this infrastructure for them that can operate from water sales, it can operate maintenance and costs. It's not a continuous drain. It's a positive impact for the local community, and that'll allows us to bring in renewable energy, new industries, sustainability, and all these other great things that you are thinking of. It's a real game changer for them and something that we can give back to the islands. But then it also is the necessary step to get this low cost power production for larger communities around them.
Yes, that all makes absolute sense. And just a final question / comment. Your Professor Yasu's diagram and your diagram showed the spin-off capabilities that aligned with the MARES approach, the power to X approach, and so on. Have you got a sort of scalability timeline in mind? Can you so if you looked into your crystal ball, in 10 years' time, will we be producing 200, 300, 400 megawatt plants? Will we have these really big scalable plants? And when do you see that timeline, those milestones being hit?
A lot of developers will tell you we'll do it next year. Ocean energy, these projects, infrastructure projects, they take time. So we're a little bit wary about saying, we can do this quickly. It'll take some time to develop and establish these projects. We have the knowledge to do a 1 megawatt OTEC facility to a 2 megawatt facility relatively quickly. If the water is available, the OTEC is simple. We have the designs, we know it well. It's something that we can bring in quickly. If they have the water available, we can adapt some of the existing industries. There's existing needs. Hotels certainly can adapt to their cooling systems to deep sea water use rather than having to redo the entire infrastructure. Smart cities, if there's plans for developing new communities that can directly apply to those kind of implementations. So there's a lot of things we can do to speed up these kind of development stages, but there are going to be some challenges. So For a megawatt scale, we expect it would take probably 2 to 3 years to do an intake facility. And as that's being done, we could do the OTEC facility alongside it. So it's not something that's going to take 10 years to put in the water, but it'll take a few years. And once we have that OTEC facility in the water, we expect at least maybe 5 years once we have the go, maybe about 5 years to do that offshore facility. And once we have one in the water, then it can really expand quickly.
So that 1 megawatt to 2 megawatt approach could be a tipping point. Thank you, Professor Yasu-san and Ben. Thank you both very much indeed. Really excellent presentation, a fascinating technology, and I'm going to be leaping onto LinkedIn after this and saying, watch this webinar because it's inspiring, and I hope one day I'll be able to get on an airplane and come over and see your site in Japan. So that is the end of our webinar, ladies and gentlemen. The recording will be posted shortly, and again, Yasu-san and Ben, thank you so much for a fantastic presentation, and congratulations on what you do. Really impressive. Thank you all very much indeed. And with that, we'll stop the recording, end the webinar, and post the event. Thank you all and a big round of virtual applause from your virtual audience.
And thank you so much for providing this opportunity for us to talk with you and answer some questions. It was a great experience from our perspective as well.
Nick-san, thank you very much.
Thank you, Yasu.
Thank you.
And have a lovely weekend. It's your weekend now as well.
You too, you too. Thank you.
Bye-bye. Bye-bye, everybody. Thank
Bye-bye.
you for joining the webinar.
You can stop recording, Jeffrey. Jeffrey, you can